All right, this is Unit 1, Day 5. Today we will be solving radical equations. We have one more lesson before our review day, and our test will be next week. So today we will be working on solving radical equations. So this first example is we would like to solve the equation the cube root of 2x plus 7 is equal to 3. And I have the steps written out here in blue. So we'll start with our original equation. And right now, on the right side of our equation, we have the cube root of this quantity 2x plus 7. So we'd like to eventually get that x by itself. So the first thing we're going to do to work towards getting that x by itself is raise both sides of our equation to the third power. So we have, when we simplify that, we have just a 2x plus 7 on the left side, and on the right we have 3 to the third power is 27. And from here it's pretty straightforward, like you're used to from prior classes. We're just working towards getting the x by itself, so we subtract 7. That leaves us with 2x is equal to 20, and then our final step is to divide by 2, giving us the solution that x is equal to 10. As we're working with radical equations, it's a good idea to check our answers. Sometimes we'll end up with solutions that don't actually work, but they sort of masquerade as if they were solutions. Like it'll pop out of your equation x equals 10, but it might not work. So I do want to go ahead and just check this and make sure it's working. Now, as I write this out, keep in mind that I don't typically, unless it's really complicated, but I don't typically formally write out this check. Usually it's a mental check or a check in my calculator, but I'm going to write this one out formally to show you. Let's see, a little too high. So our solution was x equals 10. So what I'd like to do is come back to my original equation that I started with, and where you see the x, I am going to put the 10 and just see if it works. So we have the cube root of 2 times 10 plus 7, and we're wondering, is that equal to 3? Well, if we multiply that 2 times the 10, we get 20, so we add the 7, and then we can now combine the 20 and the 7 to get the cube root of 27 equals 3, and the cube root of 27 is 3, so it is a true solution. It works just great. And again, I would probably have checked this in my calculator. Maybe right here, just typed that into my calculator. Just be careful with the parentheses and things, and see if your calculator gives you the answer 3. It should, and if it does, you know that that's a true solution. So our answer to that was x equals 10. This one's pretty similar. We've got a square root this time, and you might notice that right now we have a radical here, but then we also have subtract 5. So we want to get the radical by itself, and then we can start using powers to undo that. So my first step with this equation is going to be to add the 5 to both sides. So I have the square root of 2x plus 9 is equal to 5. Now that that radical is by itself, sometimes you'll hear people say that the radical is isolated. Once that radical is by itself, then you can use a power to undo it. This one happens to be a square root, so we want to use a second power, both sides of the equation. So we have 2x plus 9 is equal to, and 5 raised to the second power is 25. From here, it's fairly straightforward. We're going to subtract 9. So we have 2x is equal to 16, and then our final step is to divide by 2. X equals 8. Again, we want to check that, just make sure that it works. Here's my little mental check. I'm just thinking this or typing it in my calculator. Does it work? So we have the square root of 2. We are multiplying that by 8. That was the answer that we got that we're hoping is the true solution. And subtract 5. We want to know, does it equal 0? This quantity right here, 2 times 8 is 16 plus 9 is 25. And square root of 25 is 5. Does 5 minus 5 equal 0? It sure does. So we've checked it just to make sure it works, and it does. So this is a true solution to our equation. In a second, you'll see what it might look like if it's not a true solution. I'm gonna, oh, sorry. Let me get rid of this. Okay, so our next equation, it looks a lot more complicated, but it's still just a radical equation with the square root. And just with each step, think about what's happening, and we'll slowly go through and unpeel those layers until we have gotten that x by itself. So the first thing you might notice is that this equation on the left side, it's all being divided by 2. So if I want to undo that, I just want to times both sides of my equation by 2. So 2 times this and 2 times this. So when we do that, those 2's reduce. So we are left with x minus 1. Oh, my radical is super long. Plus 3 is equal to, and on the right side we have 5 times 2, which is 10. We'll keep working with this equation. The next thing you might notice is that it has a plus 3. So we're going to subtract 3 from both sides. So I have an x minus 1 under a radical equals 7. And now we've gotten that radical isolated, so we're ready to use a power to both sides to undo the radical. This is a square root, so we use a second power. So we have x minus 1 is equal to 49, and our final step is to add 1. So we have the solution x is equal to 50. The answers to these problems can be, they can be really anything. You might see big numbers, you might see small numbers. They can be negative or positive, they can be decimals, they can be fractions. Don't panic, your answers are going to be all over the place. All right, and we should always do a mental check or a calculator check. Again, you don't have to formally write your check out. It's just a great idea. So if I'm thinking about this, my little thought bubble, maybe for this one, I would probably do a mental check. It's the square root of 50 minus 1 plus 3, and if I divide that by 2, I want to know, is it equal to 5? Well, this is the same as root 49 plus 3 over 2, and root 49 is 7 plus 3 over 2. 7 plus 3 is 10 over 2, and it is 5. So, yep, that was true. It is a true solution. X is equal to 50. So this is just me over here checking my work, checking my solution. All right, next one. Here's a lovely equation. I have 2 times the cube root of x minus 3 is equal to 4. So if we're looking at this equation, you might notice that the way that it's different from prior equations is that it has a constant multiple of 2 in front of the cube root. So again, we want to get the cube root by itself. So our first step here is to divide by 2. So we have the cube root of x minus 3 is equal to, and over here 4 divided by 2 is 2. Now that the radical is isolated, is all by itself, we can use a power to undo it. So it's a cube root, so we would use the third power. Cube both sides of our equation, so we have x minus 3 is equal to, and 2 to the third power is equal to 8. You can use your calculator if you don't know that one. And we're almost finished. Our last step is to add 3. X equals 11. And this one's not too bad to do a mental check. If you put the 11 in, you have 11 minus 3, which is 8. The cube root of 8 is 2, and 2 times 2 is 4. So this is a true solution. Again, if you need to, write it out, or if you want to try to use your calculator to help you check those, you can. So why in the world are we going to all the trouble of checking our solutions? Well, with radicals, we can end up with these fake solutions. They have a name. They're called extraneous solutions. Because we're squaring both sides of the equation and variables are involved, it just could be the case that we end up with some equation that is true, but it doesn't actually work in our original equation. And it really boils down to that just because the squares of two things are the same does not mean those two things are the same. For example, negative 4 squared is the same as 4 squared, but negative 4 is not the same as 4. And sometimes it can be tricky to see where in the equation that this might be happening. But what it boils down to is you've got to check the solution and make sure that it actually works. So in our next example, we'll see one that doesn't work. So here is our equation. Oh, now it's gone. Just kidding. All right, I was going to get rid of those steps, but I'll just leave them. So our equation is x plus 1 is equal to the square root of 7x plus 15. Well, we already have the radical by itself. What makes this one different from the other ones is that we have an x both inside the radical and outside. So this equation is going to be a lot more complicated to solve than the ones that we were looking at a moment ago. So we have the radical isolated. It is already by itself, so we can start by squaring both sides of our equation. So we have the quantity of x plus 1 being squared, and the square root and the squaring undid each other, so we just have 7x plus 15 on the right. The tricky part comes into play here. We have a binomial that is being squared. So if you think back to all your prior mathiness, that's a technical term, prior mathiness, squaring something means take that thing and times it by itself. So we have x plus 1 times x plus 1. And when we have a binomial times by a binomial, we need to make sure we really carefully distribute that out. And the way that most people remember that process for distributing a binomial is FOIL. So if you remember it that way, you can use FOIL. So this x needs to be times by this x. That gives us an x squared. And we got to times that x by the 1 to get a 1x. And now we need to distribute this one. We have a 1 times an x, so another 1x. And finally, we have a 1 times a 1 for a 1. And if we combine these two x's, because they are like terms, 1x plus 1x is 2x. So we have x squared plus 2x plus 1. And then, of course, that is still equal to 7x plus 15. So we have an equation here. It has an x squared in it. It has some x terms in it. It's a quadratic equation. And if you think back to last year in our study of quadratic equations in Math 2, you might remember that the way that we solve a quadratic equation is that we we need that equation to be equal to 0. And then if it's factorable, great, we can factor it. Sometimes they're not factorable, but we're going to stick with the factorable ones for now. So we're going to bring everything on over and get our equation equal to 0. So we have x squared minus 5x minus 14 is equal to 0. And this is factorable. We're thinking of factors of negative 14. We want them to add up to negative 5, so x minus 7, x plus 2 are our two factors, and the zero product property tells us that we have two potential solutions here. Our first one is x equals 7. Now, I'm kind of skipping the part where, because most of us do this mentally in our brain, if we have x minus 7 and x plus 2 equals 0, the zero product property tells me that x minus 7 is either equal to 0 or x plus 2 is equal to 0, and we add the 7 to get the x equals 7. We subtract the 2 to get x equals negative 2. I was skipping that. I'm writing it out over here just in case you had forgotten why the sign magically changed. It didn't magically change. We just were doing this zero product property rule in our head. So we have these two potential solutions, x equals 7, x equals negative 2. It seems like they're both good, but if we actually take a minute to check, you'll see that one of them does not work. I need to snag the original. So that's our original x plus 1 root 7. X plus 15. So if we check x equals 7 in this equation, we're plugging in 7 where the x goes. We end up with 8 is equal to the square root of 49. That's a 7 times 7 plus 15. Or in other words, 8 is equal to the square root of 64. And that's true. So our solution, x equals 7, is a fabulous, good, wonderful solution. Works great. If we check x equals negative 2 in the same manner, we're going to put the negative 2 in where x was in our original equation. We end up over on this side with a negative 1. Negative 2 plus positive 1 is negative 1. And the square root of this is a negative 14 plus 15. Sorry, my handwriting, it looks like a 1 or a plus. So this is the square root of 1. Well, if we type square root of 1 in our calculator, it tells us it's 1. So we end up with this equation, negative 1 is equal to 1, which is, it's not true. It is true that negative 1 squared is equal to 1 squared, but this is false. So this negative 2 is not a true solution. It's an extraneous solution, and we want to not report it as a solution because it's not a true solution. It's kind of like an imposter, you know, it makes you think it's a solution, but it doesn't actually work. Okay, one more of these. They're very long and tricky equations, so don't feel bad if you feel like they're quite difficult. We'll keep practicing them and you will get the hang of them. So again, we've got our radical, we've got minus 7 equals x. So we can get this radical by itself by adding 7. So we have square root of x plus 9 is equal to 7. And now we're ready to raise both sides of our equation to the power, and we're using the second power here because it's a square root. So we have x plus 9 is equal to x plus 7 squared. Now remember, this is a binomial squared. This is x plus 7 times x plus 7. So if we distribute that, we get x squared plus 7x plus 7x plus 49. And if we combine these, we have x plus 9 equals x squared plus 14x plus 49. We're getting closer. We've got an x squared. So this is a quadratic equation right now. To solve a quadratic equation, we want it to get it equal to 0, and so we can subtract x from both sides and subtract 9. X squared plus 13x plus 40 is our quadratic equation. This one is factorable. I'm not going to make you deal with non-factorable ones yet. If you think way, way back to last year, you might recall that if it's not factorable, we can use the quadratic formula. The ones that we are working with in this unit, I will make sure that they are factorable ones. We will, in Unit 3, start to review polynomials and non-factorable ones. But for now, we're going to stick with factorable ones. So we're thinking of factors of 40 that add up to 13, and it is an x plus 5 and an x plus 8. So our two potential solutions are negative 5 and negative 8. We have to check those solutions and make sure they work. For the sake of the video, I am going to let you check those yourself. And the solution negative 5 works just fine. Negative 8 is extraneous. So we just have the solution x equals negative 5. Okay, one more type of equation. The type of equation that we're going to work with now looks like this, where we have a power, so it looks a lot like other things you've seen with an exponent, but this time it's a fraction power. So the reason that they are lumped in with radicals is, as you might recall, that rational exponents can also be written as radicals, and radicals can be written as rational exponents. They mean the same thing, they're just two different notations. So the reason that this is in our unit with radicals is because it could be written as a radical. In this case, the way to write this as a radical, the x minus 3 would be under a square root raised to the third power like this, and then that would be equal to 27. Maybe you're wondering where the 2 went. The 2 is the index. In this case, it's square root, so we usually don't write the 2. But it is a radical equation. You could, in theory, rewrite it as a radical and then solve it using steps similar to what we have been doing. But I think it's useful to know how to deal with it without converting it. So the way that you do that is you think about that power there, the 3/2 power, and we need to undo the 3/2 power. So what we're going to do is raise it to the 2/3 power. So I used the reciprocal there. The original power was 3/2. I'm raising it to the power 2/3. Now if you think back to exponent rules, if you have something like a to the n to the m, you would times those two powers. So here, when I times the 3/2 and the 2/3, it's equal to power 1. So I have essentially, whoops, sorry, typo. So I essentially have x minus 3 raised to the 1 power, which is really just the same as x minus 3. So we use the reciprocal so that we're turning that into a power 1 on the left. And then 27 to the 2/3 power, you could, of course, think of it as a radical. It's a third root of 27 squared. But our calculators are also perfectly capable of calculating this quantity. You just maybe need to make sure that you're being careful as you type it in. What you would type in maybe is 27 use your caret button to tell it that you want to give a power to 27. And then to be extra careful, you would maybe put parentheses around that 2/3. Some of the calculators need that, some of them don't. It's probably a good idea to just do it. Unless you know the best, you know your calculators, they're all different, but this is how I would type it in. And if you do type that in on your calculator, you should get that that is equal to 9. So we're almost finished. X minus 3 is equal to 9, so if we add 3, we get x is equal to 12. Let's try another one of these. This one's pretty similar. We have 3 times x to the 5/3 power plus 96 is equal to 0. So we're going to work towards getting this x with its power by itself, and then we'll undo that power. So maybe start by subtracting 96. So we have 3x to the 5/3 is equal to negative 96. And then we can divide by 3. So we have x to the 5/3 is equal to negative 32. And then to undo this power 5/3, we're going to raise it to the power 3/5. My parenthesis went crazy. Oh, it's linked. Sorry. 3/5. There we go. 3/5. So we have an x on this side. These powers, when I multiply these two powers together, that's just power 1. And again, you can just use your calculator to calculate negative 32 raised to the 3/5 power. And it is negative 8. This one's pretty easy to check in your calculator. I would go ahead and do that. You never know. It could end up with an extraneous solution. In this case, if there was only one solution and it was extraneous, you'd have to say that the equation had no solution. But the negative 8 works, which if you checked, you would find out. Alrighty, one last bit for these radical or rational exponents. So this this equation is very similar to the last one we did. We'll just see one small difference as we progress. So we're going to add 5. So I really want to switch to black. 4x to the 2/3 is equal to 16. We want to divide by 4 so that we have x to the 2/3 is equal to 4. And then to undo that power, right now it's a 2/3 power. I'm going to raise both sides to the 3/2 power. Now this is the first one that we've seen that has an even denominator. If you look back to the two prior ones, here when we raised it to a power it was 3/5. Here when we raised it to a power it was 2/3. Well, whoops, too far. Well, when you raise it to a power that has an even denominator, like this one's divide by 2, or if it was 3/4 or anything with an even number in the bottom, you need to introduce this plus or minus symbol. If you think back to Math 2, every time you took the square root of both sides of an equation, you introduced that plus or minus symbol. Well, it's the same reason. Both the positive and the negative solutions will work, so we need that plus or minus symbol. So we end up with x is equal to plus or minus, and if you type in your calculator 4 to the 3/2 power, it will tell you 8. So x is equal to plus or minus 8. Now in this case, there are two solutions to check. If you check positive 8 as a solution and you type in or you put it in for x in the equation, it does work. And if you type negative in, or sorry, substitute negative 8 into the equation, it also works. So both of the solutions are fine. And there's not, a certain rule about that one's right and one doesn't work, or it can be any combination if you have multiple solutions. Sometimes they both work, like this one does. Sometimes one is extraneous and one is a true solution, and it also could be the case that neither of them are solutions. Okay, one last thing we're going to talk about is when we have some really complicated equations that algebraically would be very difficult to solve. For example, this equation here, very complicated. We've got square roots, we've got a -5, we've got a -1/3. We could solve it algebraically, we could, but it's actually a lot easier to think about graphically. So this part of the equation is a simple square root graph that we've been practicing with. So we've got a square root, and then this other half, oh, that looks like the same color. Let me erase. This other part is really just, if you think back to all your mathiness in the past, it's a line. So we can think about each half of that equation as two separate graphs. And if we graph them, they look something like this, where the blue one is our square root graph, and the pink one, oops, sorry, is the line. And if we're trying to find out where the square root is equal to the line, what we're talking about is this point where they cross. So you're looking for an intersection point. Again, this is just another way of thinking about the equation. So if we're looking for the intersection point, well, our original equation, we wanted to solve for x. So if you look at the graph, the x value where they intersect is the x value 6. So the solution to the equation is 6. So let's try one of those. And this is our last thing. So we've made it. It's a very complicated day. All right, so our equation is negative square root of x plus 2 quantity plus 6 is equal to 1/2 x plus 3. Again, this equation is fairly complicated, but if we think about them separately, they're not too bad. We've got a square root of x plus 2. It's reflected. That's what the negative is telling us. And we add 6. Well, if we graph that, we go back 2, up 6. So here's our starting. And the negative is telling me reflect it. Go down instead of up. Down 1 over 1, down 1 over 3, down 1 over 5. So here's the first part of our equation. Second part of the equation, 1/2 x plus 3 is a line. Remember, this is the y-intercept. So it starts at 3, and this is the slope. So we go up 1 over 2, up 1 over 2, up 1 over 2. So there's our two equations, and you can see they intersect right here. So the solution, we're looking for an x value. These things cross when x is equal to 2. And again, we could have solved it algebraically, but it would be difficult to solve this algebraically. So solving by graphing can be a good way of thinking about it. And again, you don't always want to solve that way. It's just a cool way of thinking about it. Sometimes it's easier to do algebraic. Sometimes the graph is easier. It just gives you one more option, one more tool in your toolbox. So that is it for today. We will continue to work with equations next time, and then next week you will have review and test. So be aware that that is coming up soon. And that's all for today.